Hey nerds! Who wants to build a lightsaber? One of the most iconic images in film and one of the most fun sci-fi technologies out there. Of course, we want a sword of solid light that can cleave your enemies in one fell swoop. But how do we actually build it? Actually, better question is, what even is it? We know what it looks like in the movies. We know how it behaves on screen, but is it entirely fictional? Is there any reality to it? Or just like any ideas at all that we can play around with in real science to help us understand how to build something like this? Now, before I go any further, because I know my nerds, obviously Hacksmith made one forever ago. They actually have made a bunch of them, and they are really, really cool. And listen, if they ever need some like extra people to come and demo, like, hey, I'm Abby, I'm a physicist, and I work with plasma. Also, I've done my laser safety and my radiation courses, so, you know, let me wield the fire sword. Now, before we get into this, I do have to say this video, this is my monthly deep dive video, and it is a few days late, and I do apologize for that. I have torn a muscle, my trap, and it has been incredibly painful. So if I have any weird jerky movements, it's because I'm just about getting my mobility back, and I'm doing my best, but I also get very excited. So if I just like scream in agony halfway through the video, please do forgive me. Also, I would love to ask you to please subscribe if you haven't already. Interact with this video in some way. I'm really trying to like boost myself up there a little bit, so, you know, help me get my stuff out there a little bit more. And you can do that by hyping the video as well. I think like that's a newer feature that's been around for a little while now. So if you could do that, if you like it, and if you like what I'm doing, obviously, don't do it if you don't like it. In fact, if you're not enjoying me talking already, then just like leave. It's cool. It's totally cool. We're all different. We all like different things. We can move on with our lives. But we are here today to talk about lightsabers. So let's get into it. So there have been many attempts at creating an earthly version. But looking a bit like a lightsaber is not the same thing as doing everything that a lightsaber does. And we have to be honest here, there is like zero indication in Star Wars, like original anyway, that there is any real science behind the concept. It's literally just a light up sword. You get to do sword fights, but like make it look futuristic. It doesn't need that much thought. But that doesn't stop people like me trying to science the shit out of it. So here we are. Think of this episode as an exploration through our understanding of physics, and along the way, we'll learn about what we would need to build a lightsaber for real, or like as close to real as we can actually get. So in order to figure out what we need to build one, we kind of need to establish what the fiction says it is. And then we can try to find our way towards some reality. So what does Star Wars actually tell us? Not a lot. But originally, the lightsaber existed because George Lucas simply wanted futuristic sword fights. During production on the original film, it was called a laser sword. And there wasn't like some clever physics idea behind it or anything like that. It was literally just a sword made of light. That was enough. Over the decades, though, as the Star Wars universe expanded, people started filling in the gaps. Now, we can argue for days about what is canon and what's not canon, but the current official description gives us a bit more detail than I was expecting, if I'm being honest. There is a list of components for what's inside the hilt. We have an energy core, a focusing lens, a blade emitter, and at the center of the whole thing, we've got a Kyber crystal. The crystal is obviously where we immediately leave real material science behind, because Kyber crystals are force-sensitive fictional crystals. But within Star Wars, they are tied directly to the weapon's power and color, which sounds very lasery to me. A long time ago now, I made a video about the Death Star's laser. I will update it someday, but if you are interested in more on the giant Kyber crystals, then I will pop a video link in the description. But most interestingly that we have here is that Star Wars does now describe the blade of the lightsaber as plasma. Like Kanan, Obi-Wan, Yoda, all their lightsabers are explicitly described in the official databank as having plasma blades. And Kylo Ren's slightly dodgy crossguard lightsaber uses what are described as lateral plasma vents to stop his damaged crystal from overloading the weapon. So if we want to take the modern in-universe explanation seriously, plasma is our starting point. But if we want to take the original concept, it's just a light sword. Now, I will make the case for both of them a little bit later, but before we get to the real science chat saying like it's plasma or it's light or whatever, that doesn't actually explain how a lightsaber works. So we have to look at what the thing actually does.
The original concept was that the Jedi would fight with swords, and then I wanted to make it a futuristic kind of sword, so I made it a lightsaber, which is sort of a laser sword.
So when you switch it on, whatever comes out of the hilt travels about a meter and then it just stops. There's nothing at the other end to cause the stop, like a second emitter or a physical cap, but the blade clearly has a defined width and a defined tip, and unless someone is dramatically destroying it, it stays in that shape. It also stays attached to the hilt when you move it. Sounds simpler than it actually is. You can swing it around very quickly and the blade doesn't trail behind like fire from a torch would. It moves as if it's all part of one solid object. Then there's the obvious bit. It's hot enough, or at least it transfers enough energy to cut through people, droids, and really thick metal. In The Phantom Menace, Qui-Gon can push his blade into a blast door and heat a fairly enormous chunk of it until it is glowing and melting. So there is a lot of energy being transferred when the blade touches something, except apparently not when it doesn't, because people can like just stand centimeters away from these things. Like they hold them right beside their faces. Their robes don't catch on fire and the air around them isn't like glowing white hot. Nobody in the Star Wars universe is wearing eye protection unless they're a stormtrooper. There is zero safety protocols in a galaxy far, far away for these Jedi. So whatever is carrying all of that energy is also very well contained. And one more necessary bit of behavior is that two lightsabers will clash against each other. They don't merge into one bigger like blob or like pass through one another. They do behave like physical swords. So in our quest to build a lightsaber, we need to meet a few conditions. We need an energy source like the Kyber crystal that Star Wars gives us. We need some way of creating the blade. We need a way to confine it and decide exactly where it ends. We need to prevent all of that heat and energy escaping sideways. And we somehow have to give the blade enough structure that another lightsaber can hit it. Star Wars doesn't really need to tell us how any of that works because, you know, it's fiction. It's totally fine. I'm down for it. Don't complain. I, unfortunately, though, have decided to try to explain how we could build a freaking thing. So, this is what we're going to do. And I think the easiest way to do this is to take the requirements one at a time and then just see how far real physics can get us. So let's start with the original idea. A sword made of light. My dream. If we want a beam of light that can carry a lot of energy in one direction, then the obvious real-world technology is a laser. And actually, quite a few of the things that Star Wars gives us fit really nicely with that idea. There's an energy source in the hilt, there's a focusing system, an emitter, and a colored beam coming out the other end. That is at least vaguely laser-shaped as a concept. Now, a laser is created when light is amplified through the stimulated emission of radiation. What comes out is basically a very organized beam of light. Normally, when something emits light, like the photons are traveling in lots of different directions and they can have a range of different wavelengths. In a laser, we use something called stimulated emission to create photons that are matched in frequency and phase and then send them in the same direction. That gives us this very narrow beam and we can design it to stay collimated over really long distances. Collimated just means that the light stays in roughly a straight line for quite a while before it starts to spread out. Another key feature for us is that lasers can carry a lot of energy. We already use them industrially to like cut or weld materials. If you focus enough laser power onto a small enough area, you can heat the surface until it melts or vaporizes. So if all we wanted was something coming out of a handle that could burn through metal, lasers are a totally reasonable place to start. Now, I also want to briefly point out here that the first laser was actually created in 1961, which was just 14 years before Star Wars was made. So this was like really new technology at the time. The problem, though, is that we don't want a laser gun, we want a sword. And one major issue with light is that it has no mass. It's not solid. Two laser beams don't hit each other. The beams can cross, and light is a wave, so overlapping beams can produce interference patterns. But after they overlap, they just keep going. Now, there are some exotic quantum interactions where photons can interact with photons, like our research group at Oxford has published papers on photon-photon scattering. But we are talking about effects so weak that we would need ridiculous electromagnetic fields and extremely high energy experiments to even study them. And this is just light scattering, not light acting like a solid. It is absolutely not giving us Obi-Wan and Anakin pushing against each other over a lava river. So a normal pair of laser beams would just pass right through each other. But I was thinking about this. I actually think that would be a really interesting choreographed fight scene. Think about how would they actually play out if the beams don't meet each other, but if the beam touches you, you're screwed. So how do you judge where to be? I don't know, I just think it'd be cool to watch. Anyway, I digress. Now, an interesting thing is that light does actually carry momentum, which can apply a pressure when that momentum is transferred to an object. This is how something like a light sail will work. But the pressure it produces is tiny, and it's in the direction of travel of the photons. So it would be towards the tip of the lightsaber, not transversely, which is the sideways direction, the directions where the beams would clash against each other. Now, another challenge with the lightsaber shape as well is, of course, the length. If I point a laser across a room, the light doesn't just travel a certain distance and then just decide it's reached a desired length and disappear. The light is physically moving and it keeps going until it either hits something and then it gets absorbed or reflected, or until it spreads out so much that the beam gets really big and the intensity becomes insignificant and you can't really see it anymore. I was remembering, do you remember the Flat Earth documentary? Do you remember the guy at the end with his and his beam, and he didn't understand that light diverges and he was trying to prove that the Earth was flat, but obviously they kept proving that the Earth was round. It's really funny. You should watch it. Anyway, now we could maybe put something at the end of the lightsaber to stop it, like a mirror, for example, that would reflect the beam back towards the hilt. But then we'd need another mirror at the hilt to stop the energy from damaging the stuff inside it. But also then, how do we hold a mirror a meter away? You'd have to have some kind of physical rod between the hilt and the handle. And without something at the far end, there just isn't a way to make a beam of light have that nice rounded lightsaber tip. And there is one other thing that goes into the cons box. It's actually surprisingly hard to see a laser beam. We can see the point where it hits something, but that's because the light scatters back towards your eyes. And we can see the path if it moves through something like smoke or fog, because again, the light is scattering from all the little particles suspended in the air. That's why laser shows fill the room with haze, and it's also why they tend to be in the dark. Because bright daylight or room light will be stronger than the scattering effect of the laser itself, no matter how powerful it is. So we can get the cutting part, and we could get something coming out of the hilt that is genuinely made of light, but we can't get the solid blade, we can't cut it off at the right length, and we probably won't be able to see it. But we can get around some of these issues if the laser is powerful enough to ionize the air and create a glowing plasma along its path. But then the thing we're seeing isn't the laser, it's the air reacting to it, which very nicely brings us back to the explanation Star Wars eventually settled on. Plasma. So, can we make a plasma blade? Well, plasma is definitely a better option if we want something that actually occupies the space in front of the hilt rather than just light traveling through it. Now, plasma is known as the fourth state of matter after solids, liquids, and gases. Basically, if you give a gas enough energy, you can start knocking electrons away from the atoms, and then you end up with a mixture of positively charged ions, free electrons, and usually there's some neutral particles hanging around in there as well. Now, one very useful thing about plasma for us is that it can emit its own light. See, the electrons and the ions are constantly interacting and colliding, and those collisions can excite atoms and ions into higher energy states. And then when they drop back down again, they release that energy as photons. Electrons can also recombine with ions and then emit light in the process. So unlike our laser, where we mostly only see the beam because some of the light gets scattered towards us, the plasma itself can actually look like it's glowing. Now, the exact color as well depends on what the plasma is made from and how energetic it is, because different atoms and ions will emit particular wavelengths of light. This is already a big win for our lightsaber. We wanted a blade that is visible from the side. Also, plasma is made from charged particles, which means it responds really strongly to electric and magnetic fields, and that is going to become very useful for us later on. Now, plasma sounds very exotic. I remember when I first heard the term in it was Star Trek Next Generation, and I thought it was fake. And now I'm a plasma physicist, lol. But so this fourth state of matter idea just sounds really kind of like, ooh, because we don't interact with it every day. But plasma on the scale of the universe is the most common form that matter comes in. A lot of that is down to stars, because most of them are giant balls of plasma. Now, on Earth, lightning produces plasma, and the aurora that we see in the sky involves plasma, and we do create it deliberately all the time, most commonly for neon and fluorescent lights. So you likely sit underneath rods of plasma every day. Also, I just want to give a slight correction to the way that plasma often gets talked about online, because plasma doesn't automatically mean that it is unbelievably hot. You can actually make low temperature plasmas where the electrons are very energetic, but the gas itself is cool enough to interact with biological tissue. There is an entire area of research in plasma medicine doing exactly this. Also, though, blood plasma is an entirely different thing. It has absolutely nothing to do with this plasma. They just use the same word. That probably gets confusing then when you talk about plasma medicine, because entirely different things. They have no relationship to each other. Now, for our lightsaber, we don't want cold plasma. No, we want the kind that can cut through a door. And we already have that. Plasma cutters are used industrially to cut through metals. And the basic idea of this is fairly simple here, right? You start with a gas, usually something like air, nitrogen, or some argon mix. It depends on the system. And then you force it through a small nozzle. An electric arc will give the gas enough energy to ionize it and then form the plasma. The nozzle constricts the flow into this fast, narrow jet, and then that plasma can reach temperatures of tens of thousands of degrees. So when it hits the metal, it melts it, while the high-speed gas flow blows this molten material out of the cut. Now, we actually talked before a bit about plasma and magnetic nozzles for directing it when we covered the fusion drive in The Expanse. I'm kind of hoping with all of these episodes and all of these deep dives that you guys are starting to see where all of these ideas in physics kind of can start to overlap and give us all these different technologies. But coming back to our lightsaber, there are, of course, some obvious differences between a plasma cutter and what Luke Skywalker is carrying around. Like, the plasma cutter isn't just sitting there in front of the torch. Gas is continuously flowing through the system. New gas comes in, gets ionized, shoots out through the nozzle, transfers energy into the target, and then disperses into the surrounding air. So similar to the issue with the laser, the blade is really just this continuous stream of material. And in most plasma cutters, the metal you're cutting is actually part of the electrical circuit. Like, so the arc starts at an electrode inside the torch and it transfers through the plasma onto the workpiece. So if the electrical connection to the workpiece isn't there through like a grounding cable, then the normal cutting arc doesn't work properly. That is obviously a little bit inconvenient for a lightsaber because like they don't have time to attach like this grounding lead to the stormtroopers before chopping through them, no matter how bad their aim is. Now, there are plasma torches where the arc stays inside the torch and you get a hot plasma jet coming out, which I think is what Hacksmith ended up making. So we don't necessarily need to give up here, but either way, what we actually have made is a jet. And jets behave like jets. Their shape depends on the gas flow. It depends on the pressure, the power that is going in, and whatever atmosphere they're operating in. We can make plasma jets that extend out into open air, and there is a lot of research into like controlling their length and their shape. But the glowing plume is still a moving, interacting gas. It doesn't have like a hard edge where the plasma exists on one side and then suddenly like stops on the other. Also, the visible length of a plasma jet doesn't necessarily tell you where the useful cutting power is. So we can make like long atmospheric plasma plumes that are actually really cool. And as I said earlier, like some of them are designed specifically so they can be used on people without burning them. So just because you have managed to make a meter-long glowing plasma plume does not mean that you have made a meter-long metal cutting blade. And then we have the movement. You see, if I have a torch throwing a hot gas out in one direction and I start swinging that torch around the place like I'm fighting Darth Maul, the gas already leaving the nozzle has inertia. It doesn't suddenly know that my hand changed direction. The plume is going to bend and distort. The tip of the plume isn't attached to the hilt, so it's definitely not going to move like a sword would. But plasma does get us further than our laser. It gives us actual matter in the blade that can glow and interact with the atmosphere. But can we make it cut like a lightsaber? There's a bit of a difference between an industrial plasma cutter moving through a steel plate and Luke Skywalker swinging through something in a fraction of a second. And it's not really about temperature. We tend to think of lightsabers as being incredibly hot, and obviously whatever is doing the cutting needs to be hot enough to melt or vaporize the material. But temperature alone doesn't tell us how much cutting it can actually do. What we actually care about is power. How much energy we need to transfer into the material and how quickly we can transfer it. The faster we want the cut to happen, the more power we will need. So let's imagine that I want to swing my lightsaber through a steel plate that is 1 centimeter thick. We don't have to melt the whole plate, just create a channel where the blade passes through. Now, depending on which shot you look at in the movies, the blade is somewhere around like 1 to 2 inches across. So let's be kind and use the smaller end, like a 1 inch or about 2.5 centimeter cutting width. If the blade travels 1 meter through a steel sheet that is 1 centimeter thick, which to be fair, guys, come on, that is really thin. We're being really generous here. The strip of steel that we need to melt weighs almost 2 kilograms. So even with our completely perfect lightsaber, we would need about 2.6 megajoules of energy just to melt enough steel for the blade to get through. But speed also matters. Because sure, if the cut takes 1 second, then we transfer the 2.6 megawatts into the steel. But guys, if you want some really nerdy stuff about swords, I mean, who doesn't? I found this website, right, called Sword STEM, which is all about science applied to sword martial arts. Come on, seriously. They did a bunch of tests, and the result was that a sword swing is about 20 meters per second. So if we want to slice through our 1 meter door like it's a hot knife through butter, then it is about 0.05 seconds, meaning we would need to deliver about 52 megawatts. Now, a normal handheld plasma cutter will run at around 7 to 10 kilowatts. So we need about 10,000 times the power running through something that we are holding in our hand. And guys, I am still being fairly nice to the lightsaber here. Like, I gave it a really thin door, come on. Also, this is a rough, idealized calculation where nothing is lost. But in reality, the actual power requirement would be significantly higher. This is the main difference between our plasma cutter and a lightsaber. Like, the industrial cutter can take its time. A lightsaber has to dump all of that energy into the material almost instantly. Now, there is also another complication. Lightsabers seem to cut anywhere along the blade. And you see, with a plasma cutter, all of the useful energy is concentrated at the torch, it's at the tip of it. But with a lightsaber, you can hit something with the middle, the tip, or right next to the hilt, and it will have the same effect. So whatever is producing this blade has to keep a stable and even amount of energy available along the full length of the blade. But to be fair, what we actually care about here in our little analysis is that the actual cutting part that we've talked about doesn't need any new physics. We know how to melt metal, we know how to use plasma and lasers to cut things, and if you give me enough energy and enough power, I can destroy things for you. I mean, I won't, but I could. Because I know the nerds, I know what you're thinking. I know you're thinking. You're thinking, where does all the heat go? Because our lightsaber is a bit of a health and safety nightmare, let's be real. Just because we calculated something like 50 megawatts going into the steel during a cut does not mean that the blade itself has to be radiating 50 megawatts into the room at all the time. That power is what we need to transfer into the target during contact. How much energy the blade is losing to its surroundings depends on what the plasma is made from, its temperature, its density, and how efficiently we manage to contain it. But it definitely won't be zero. Now, we've already established that one reason plasma is useful for us is because it emits light. Unfortunately, visible light is not the only radiation a hot plasma can produce. Depending on the plasma, you can also get a lot of UV and infrared radiation, which is one of the reasons real plasma cutting and welding needs proper eye and face protection. A lightsaber, meanwhile, spends quite a lot of time a few inches from somebody's face. The magnetic fields we're going to talk about later can help to control charged particles, but they can't trap the photons. Once the plasma produces light, that radiation can just leave. Now, we could choose our plasma parameters so that it is most strongly emitting in the visible light region. It doesn't completely get rid of the radiation, but we could have manageable levels. The amount of radiation, though, is also going to be affected by the amount of material. So if we had a low density plasma, then we can still have a fairly bright beam with less radiation, but that also means less energy. Ideally, what we want is a system that is low energy until it's in contact with something. We want some way to create a response to a hit so that the power is concentrated on and delivered through the contact point only. That keeps the blade wielder safe, kind of like a real sword. There is, of course, nothing in the real world that I can think of that can do this, but we have bigger problems. You see, no technology is 100% efficient, even in a galaxy far, far away. Some portion of energy always gets lost in the system, normally as heat. But let's imagine that we somehow build a lightsaber where only 1% of the power is lost. 1% of 52 megawatts is still 520 kilowatts. Now, the cut only lasts about 0.05 seconds, so that would be around 26 kilojoules of waste energy. But our lightsaber tech is all contained inside the hilt. This is a lot of heat to suddenly dump somewhere inside a handle that you are gripping with both your hands. Now, we could talk about cooling systems, but that doesn't make the heat just disappear because a cooling system just moves it somewhere else. Cars have radiators and computers have fans and heat sinks. We're talking about like power station levels of energy here, where they have enormous cooling towers. Our lightsaber is a metal tube about the size of a large torch. Now, guys, obviously a movie isn't going to worry about this. Like, they have to be practical for the purpose of the story. You have to be able to hold the hilt and have the blade like right behind your head in your fight stance without worrying about the radiation frying your brain or your arm being incinerated by all the waste heat. I am not complaining. But in terms of what we're doing here, we are starting to face the very real problems with our lightsaber. While we can absolutely reduce the radiation hazard by using a lower density plasma, in order for the blade to behave like a blade really does in the Star Wars universe, we need to create some new system that will allow for the density and power to massively increase when the blade makes contact, and for that energy to be transferred without wasting any heat into the hilt, or have like a seriously special heat-resistant material that protects the sword holder. Unfortunately, these are two problems that we just can't solve with our current physics, and I am sorry to say, you guys, we're just getting started down that path. Now, something that we haven't talked about yet is how we actually shape our plasma blade. So far, we just have like this jet streaming out of our handle. What we need is a way to confine and shape the jet, and we can do that using magnets. Magnetic confinement is a very real thing. Like I mentioned, we talked a lot about this in the fusion drive episode. Plasma contains charged particles, and charged particles respond to magnetic fields. A particle moving through a magnetic field tends to spiral around the direction of that field, which means we can use magnets to stop the plasma simply spreading out sideways. A magnetic field is very good at stopping charged particles moving across it, but the particles can still travel along it. So if we make a straight magnetic field running along the length of our lightsaber, this can help keep the plasma narrow, but all the particles can still stream straight out of the end of it. Now, there is actually a real solution to this, and it's called a magnetic mirror. Instead of making the field equally strong along the whole plasma, you make it much stronger at either end. And then as particles spiral into that stronger field, their motion slows and reverses, so they then bounce back into the middle. People have built fusion experiments based on exactly this idea. Now, a magnetic mirror isn't perfect, of course. Like, some particles always have the wrong trajectory and they'll escape through an area called the loss cone. But for us, a slightly leaky lightsaber is the least of our problems. The much bigger problem is where we put that second mirror. Now, a normal magnetic mirror machine has strong magnets at both ends of the plasma. We can put one in the hilt easily enough, that's fine. The other one, though, needs to be sitting about a meter away where the tip of the lightsaber would be, which once again gives us the option of putting a physical rod through the middle of the blade to hold the magnet there. But, guys, I'm actually wondering, is this even a problem at all? Like, why can't we have a central rod? Think about it this way, right? Think of something telescopic that pushes out the second magnetic mirror, but we just can't see it because of the plasma. I think that this might actually be the best solution here, but I'll talk more about that in a little bit. So now, right, we know what the missing technology actually has to achieve. It isn't just like really strong magnets. We need a way of remotely closing and stabilizing the plasma at the tip, probably while actively controlling the current and magnetic field along the blade. And so far, we have found our way to something hot, glowing, and approximately blade-shaped, but it still isn't a sword. Right, so let's say we have somehow managed to confine the plasma into a meter-long blade and keep it there while we swing it around the place. What happens when two of them hit each other? Now, the obvious problem, like the laser, plasma's not a solid. If you fire two plasma streams at each other, there isn't one universal outcome where they just like bounce apart. Depending on the density, temperature, speed, and magnetic fields involved, the plasmas can mix, and they can slow each other down, they can form shocks, or just become unstable. Plasma, you guys, plasma loves some instabilities. Now this is interesting plasma physics for me, but not really sword fighting. If we want the blades to actually stop each other, then the magnetic fields we are already using for confinement are probably our best chance. So could two magnetically confined plasma blades repel each other strongly enough that they feel solid? Potentially. I'm reaching a bit, guys, but look, we're just going to go with it. At least in terms of force, magnetic fields can exert pressure, and when two magnetic structures are pushed together, it can produce a force between them. Now, as a rough scale here, right, if we wanted about 100 newtons of force between the blades over an interaction area of like 1 square centimeters, the magnetic pressure works out to a field of about 1.6 Tesla. That is a strong magnetic field, but it isn't some like absurd, crazy sci-fi number. MRI machines operate in the Tesla range, and experimental magnets can go much higher. Producing a noticeable repulsive force between the blades might not be the hardest part here. The hard part is making that force behave the way like a sword would. So a magnetically confined plasma is still a fluid. If you push on one part of it, it can move around and like rearrange the magnetic field. So like having enough magnetic pressure to push something away isn't the same thing as having like a straight edge on a blade. I was thinking about this as like, say it was like a memory foam blade or something, you know, like when they clash, they might push on each other, but then they both deform in the process. Also, truthfully, magnetic fields don't always repel each other. Like the interaction depends on how the fields are oriented. When you bring two magnets together one way, they might repel, but if you turn one around, well, then they can attract. Lightsabers don't seem particularly bothered about orientation unless we were to like accept that that's what the difference is between the blades of the Sith and the Jedi, but I just don't think that that actually works. So our containment field now needs to recognize another blade and create a stable repulsive interaction regardless of how the two weapons meet. Now, something else that I hadn't really thought about before is that we still need the force of the clash to actually reach your hands. So when two normal swords clash, the force travels through the solid blade into the hilt. You feel it in the hilt. Because our lightsaber doesn't have a solid blade, if another lightsaber pushes against the magnetic field near the tip, the confinement system has to have a way to transfer that force all the way back into the hilt. And then all the machinery in the hilt has to be able to survive the feeling of it. So our field has to create a boundary around the plasma that acts like a solid, transferring forces to the hilt, and then work no matter the direction of the incoming blade. At this point, you guys, saying it's a plasma is just the easy part. I'm going to be honest with you here. I am ready for us to just rip off Rimmer's hard light drive and just call it a day.
Your hard light drive's tougher than Vindaloo mutton.
So, let's talk about how Star Wars says the lightsaber works. The official description is that there is a power cell or energy core, a focusing system, a blade emitter, various controls, and obviously the Kyber crystal. Now, the Star Wars databank describes an energy core powered by a Kyber crystal, while another official explanation says that the power cell powers the weapon in conjunction with the crystal. So look, I don't think we're going to get a perfectly consistent electrical diagram or anything out of this, but clearly they are both important. The power source, that's easy enough conceptually for us because, you know, we need one too. Although we've already established that it needs to deliver an absolutely stupid amount of power. But then they have a focusing ring or focusing lens and a blade emitter. Now, the official explanation says that the focusing ring aligns the Kyber crystal so that it can emit the blade. And if it isn't calibrated properly, the crystal can crack or the lightsaber can actually explode. And this is why I want to bring the laser back. Now, if you told me as a physicist that you have an energy source, a crystal, focusing optics, and an energetic beam, I would immediately say, well, that's a freaking laser. Crystals are genuinely used in lasers as the game medium. Now, one really common example is an Nd:YAG laser. This is where neodymium ions are embedded inside a yttrium aluminium garnet. I can't say yttrium and aluminium together at the same time. Yttrium aluminium garnet crystal, Jesus. So you put energy into that material, excite the ions, and then use stimulated emission to produce laser light, then optics control and shape the beam. Now, guys, come on. This doesn't mean Star Wars has secretly given us a scientifically accurate laser diagram here. It hasn't. The official description calls lightsaber blades plasma, and Kylo Ren's lightsaber is explicitly described as splitting a plasma stream into 3 channels. But it does give us some interesting pieces to play with when we try to build our own version. The really fictional part is the Kyber crystal itself. Now, Kyber isn't there just to determine the blade color. In Star Wars, it is fundamental to how the weapon works. And larger Kyber crystals are also used in things like the Death Star super laser, as I mentioned earlier. So apparently, they have some fairly serious energy handling properties. They are also attuned to the Force. Jedi traditionally travel to places like Ilum to find one, and the crystal becomes connected to its Jedi and then develops its color. And if you're Sam Jackson, that means you get a purple one. Now, Sith instead bleed the crystal using the dark side of the Force, which corrupts it and turns it red. Now, for us, real crystals can do some genuinely useful things, not healing. They can act as laser gain media, alter light, exhibit piezoelectric effects, and they have all sorts of optical and electrical properties. So using a crystal as part of an advanced energy weapon is perfectly reasonable as a starting point. We just can't make one that communes with the Force. Now, to be clear, of course, you don't need to be Force sensitive to switch on a lightsaber, like plenty of non-Jedi have used them, but Jedi use the Force to anticipate attacks and move with ridiculous precision, which probably helps when you're waving an extremely dangerous plasma sword around next to your own limbs. So, Star Wars gives us a power source, crystal, focusing system, emitter, and then it allows the blade itself to have the properties that the story needs it to have. It's the anthropic principle, but for plasma swords, which is fine because it's fiction. Guys, I'm totally cool with it. We don't have Kyber crystals, and I am devastatingly unable to use the Force. But after everything that we've learned, I think that we can actually come up with a design that gets us pretty close. So, here's my proposal for a lightsaber. Okay, we've spent this entire video taking the lightsaber apart, so I think it's only fair that we actually try to put one together. And I'm going to allow myself one compromise straight away. I think our lightsaber needs a physical spine. You see, if we had a very thin telescopic rod extending from the hilt, this will solve a few problems for us immediately. Most importantly, it gives us somewhere to put the second magnetic mirror. So instead of needing all of our magnets to sit inside the handle and then somehow create this fictionally perfectly shaped magnetic bottle a meter away, we can put magnetic hardware at both ends and then use the rod itself to carry conductors and control systems along the length of the blade. We could even embed smaller coils or current carrying conductors along the telescopic sections to help shape the field between the two ends. So already our magnetic confinement problem has gone from invent a completely new kind of remote field to build a ridiculously complicated telescopic electromagnetic structure. I get that it's still hard, but I swear we've solved something here. This is an improvement. The rod also gives the blade an exact length and conveniently gives us a physical connection between the tip and the handle. So when two lightsabers hit each other, some of the force can actually be transmitted through the spine rather than unrealistically needing the magnetic field to do absolutely everything. Obviously, now we have a rod in our energy sword, but I don't think you would necessarily see it. See, as the rod extends, we could fire very intense laser pulses along it using our Kyber crystal and ionize the surrounding air. Okay, not our Kyber crystal if we're talking about a realistic one. It's a real crystal, but you know where I'm going from. Basically, as it extends, you're ionizing the surrounding air, creating our plasma channel around the spine. High power lasers really can ionize gases and create long plasma channels through air. This is pretty close to my own research field. Like, I work on laser plasma interactions for creating wake fields for particle acceleration. But look, I mostly focus on imaging these structures. So the crystal is the gain medium that creates our high power laser. Okay, I have to give a little side note here. There is absolutely no way that we could create a powerful enough laser in such a small space with our current technology. But we're thinking way into the future, a long, long time ago, far, far away. We're cool. Okay, look. Anyway, the laser pulses would create the plasma around our central structure, masking the rod as it's extending out inside our plasma jet. Then we use our magnetic field to stop the plasma immediately spreading away from the rod and continue pumping energy into it to keep it ionized and glowing. So visually, you press the button, the thin spine telescopes out, and at essentially the same time, the air surrounding it lights up as plasma. If the plasma is bright enough and the rod is thin enough, what you see is the glowing blade extending out of the hilt. It's pretty lightsaber-y, you guys. Come on, I'm really proud of that. Now, the plasma is still doing the cutting for us as well. Like, we already know how to transfer huge amounts of energy through plasma into a material. Our problem is doing it ridiculously quickly. So when the blade makes contact with something, the power system has to dump a huge burst of energy into the plasma around that region. Now, we worked out earlier that one of our fast cuts needs a hell of a lot of power in a very short amount of time. Storing energy isn't the main challenge here, though. Releasing it is. Like, what would help us is if we had some kind of pulse power system, essentially a very advanced capacitor bank, which then releases that energy in a short burst when the blade needs it. This is how plenty of real high energy physics experiments work. You build up energy relatively slowly and then release an enormous amount of power very quickly. Our problem is scale. A real capacitor system storing megajoules is nowhere close to fitting in a lightsaber handle. So that part needs an absolutely heroic amount of future miniaturization. But at least the architecture itself makes sense. Now, we can do something similar with the heat as well, right? So rather than somehow trying to radiate all of the waste heat away during a fraction of a second swing, we could temporarily dump it into a thermal store inside the hilt, something like a heatsink or a phase change material, and then get rid of it more slowly afterwards. Again, very real idea, but to be very clear, it's a completely unreasonable scale. Inside the hilt, we have an energy store, a pulsed power system, a high power laser, and the controls for the plasma and magnetic fields. Coming out of the hilt, we have a thin telescopic spine carrying the magnetic hardware, probably some of the electrical connections, and the second magnetic mirror at the tip. Surrounding that spine then is the plasma blade, created from the atmosphere using the laser and held roughly in place by the magnetic field. Now, some of you eagle eyes, some of you, I know it, might have noticed that this gives us one obvious limitation. In a vacuum, there is no air to ionize. So if we want lightsaber fights in space, we need to carry our own gas and then feed it along the spine as well, because you know, my lightsaber wasn't complicated enough. Now, to be clear, I agree with you. I agree with you. This is cheating. I'm cheating, totally cheating. This is absolutely cheating in comparison with the fictional version. There's a physical object inside the blade. Like, my power system doesn't currently exist at anything close to this scale, and keeping that plasma stable while swinging it around would still be an enormous engineering challenge. But I actually think it's pretty close. Most importantly, though, and any of you return viewers will know this is what's most important to me. Almost every part of our description so far is based on physics or technology that already exists in some form. We didn't have to invent anything new this time. We have just combined all of it into, okay, fine, an absolutely deranged plasma sword, but it's all real.
If you strike me down, I shall become more powerful than you can possibly imagine.
So where does that leave us? Well, A surprising amount of my proposed lightsaber is based on things that we can already do. We can make plasma, we can create it with lasers, we can guide charged particles with magnetic fields, we can build telescopic structures, and we can store large amounts of energy. What we can't do is any of it at the size, speed, and power that a lightsaber needs. The power system is probably the biggest engineering problem. Like, we need to store megajoules of energy and then release a significant chunk of it in hundredths of a second from something that fits inside a sword handle. Now, we know how to make pulsed power systems that do that kind of thing, but they are not remotely this small. Then we need the materials. Our telescopic spine has to survive sitting inside very hot plasma. It has to carry the magnetic and electrical hardware, extend and retract repeatedly, and still be strong enough to behave like a sword. Again, none of those requirements individually demand new physics, but putting them all into one skinny retractable structure would require some spectacular material science. The plasma control is somewhere in between. Magnetic mirrors and active plasma control are real, so I don't think we need to invent a completely new force of nature. But keeping a meter-long plasma blade stable while somebody is like swinging it around is far beyond anything that we currently know how to engineer. And I think that the messiest unsolved bit of this whole thing is still the energy transfer. We need the plasma to sit centimeters away from your body without roasting you, but when it touches a door, it needs to transfer tens of megawatts into the material almost immediately. Now, like I said, we can reduce the problem with the low-density plasma, magnetic confinement, and careful control of when we dump power into it, but I don't have like a real mechanism that gives us that perfect lightsaber behavior. And if we want to get rid of my telescopic rod completely and build the actual Star Wars version, then we are back to needing something much more exotic, like a freestanding field that can form a rigid, meter-long boundary in open space, stop another lightsaber, contain the plasma, and somehow control what energy is allowed to cross it. At that point, we really are talking about something closer to a science fiction force field. Guys, can we all say Holtzman field? Come on. So, I think that there are like two answers here, right? Could we build something that looks and behaves somewhat like a lightsaber using extensions of real technology? Maybe. Give me absurdly good batteries, pulsed power, advanced materials, and plasma control, and I think my slightly cheating telescopic version is at least a concept that we can describe with known physics. Could we build the actual thing from Star Wars? No physical blade, completely retractable, safely contained plasma that cuts through basically anything and clashes like a solid sword? For that, we still need to invent the bit that makes a lightsaber a lightsaber. Or, you know, find a Kyber crystal. Like, that might actually be easier.
Nothing more will I teach you today.
Nerds, thanks for watching. What did you think, though? I genuinely want to know, like, what solutions have you come up with for some of these problems that we've talked about? Or what problems have I completely left out? What's your favorite lightsaber? And obviously, what color is your lightsaber? I mean, mine is purple, for sure. Now, please do subscribe if you haven't already, and like this video and stuff so that more people can see it. And if you did like this video, then you might like my video all about Stargate's 0-point modules. Or you can check out my monthly deep dive playlist here. And if there are any topics that you want me to break down, then please do let me know in the comments. And as always, stay nerdy.